let's look at some specific examples of these. Our descriptive analytics, basically we're trying to understand where we are. So in addition to those summary statistics, we may use some filtering or data reduction, because we don't necessarily care about all the data. We only care about the data that's relevant to our decision process. If you think about last Wednesday's lab, the very last step after you had converted all of the Oklahoma data into the common data model was to filter out most of it, because we only care about the transactions related to Oklahoma State University, not all of the entire state transactions. So we filter on the things that are relevant to our decision-making process. We also did some joining where we were matching up data on specific values, primary keys and foreign keys. We can also do things to match values, for example, to make sure that all of our invoices match purchase orders that were actually sent. We're not just paying for things that we didn't order. And under matching, there's a special category called fuzzy matching, which takes it a little bit more in depth than just a straight one-to-one match, because we know that 100 north and 100 N period are the same thing, right? You and I know that that's the same address. A computer does not. They are not equivalent because they are not the exact same data value. And so a computer would say, oh, those are two completely separate addresses. So what fuzzy matching does is fuzzy matching goes a step beyond, and it looks at a probabilistic match. It says, okay, these are 70% similar because they share 70% of the same character between these two. Just like in the example here, I've got Richardson Street versus Richardson Street. So we would use this to try and find, for example, employees who have created fictitious vendor accounts so that they can send in invoices and embezzle money from the company. The employees trying to be clever, they know that the data is not going to find an exact match, so they change their data, introduce data quality issues to try and conceal their fraud. But we can use tools like fuzzy matching to find the ones that are likely to be the same thing. Not everything that's going to be fuzzy match is going to be exactly the same thing, but it helps filter the data. It reduces it to the ones that are the highest risk, so we can focus our attention on the things that represent risk. And as an auditor, we care about risk, whether you're an internal auditor or external auditor. As a business process manager, you care about risk. Descriptive statistics are essentially just looking at that. Now, diagnostic, I'm going to give you some examples of diagnostic analytics. Again, with each of these, we want some sort of benchmark to compare, to figure out whether it is good or bad. We're passing some sort of judgment or making some sort of decision. Do we need to correct something here? Do we need to push our salespeople a little bit more so they can meet that sales goal that we had set? Okay, so the first one here, this is looking at average days to ship for different categories of products that are being produced. Do you remember a Z-score from your statistics class? For the concept of a Z-score? Here's basically what it is. You have a normal distribution, bell curve. Normally, in the middle here, you would find your mean, and then everything would be some deviation from the mean, right? You have standard deviations. With a Z-score, what we do is we set the mean to 0, and then we say this is +1 standard deviation, +2, +3, -1, -2, -3 standard deviations. Now, the key thing about this is that within 3 standard deviations of the mean, what percentage of my observations are going to fall in there generally? 99.7. So 99.7% of all of the observations are going to be within 3 standard deviations of the mean, which means that if I have something that is 3.1, we would consider that an outlier. Very, very rare. 1 or 2 chances in 1,000 that would happen. So outliers matter. If we look at this data here I have in the middle my Z-score of 0, and then I've got my standard deviations. I've got a 1 and a 2 and a 3. So looking at this, these observations here, these are ones that are very, very rare. All the rest of the stuff, this is normal activity, although these ones are getting, more rare. But those last ones, those outliers, those represent potentially a problem. I want to focus my efforts as a manager, as an accountant, on those to figure out, okay, how can we improve the process for those? If this is a customer that is waiting 2 weeks to get their product, what's the risk to the business? They don't come back. They're like, yeah, we'll go somewhere else that's going to get us there in 2 days instead of 2 weeks. Okay, so we don't want to lose the customers in these cases. So we care about those outliers so that we can identify those and make decisions to improve or fix the problem. Improve the process. Give that customer incentives. Give them a discount on their next order so that they're happy and will come back to us when we can give them better service here. Z-scores. Basically, that's just a benchmark. We're profiling the data to figure out how an individual observation compares to the mean. Another example here. Here we have variance analysis. You remember this from managerial accounting, right? So you had your budget and your budget variance. You can get down to the point of having standard cost and standard volume, and you look at the individual components that are driving those variances. Here I have a benchmark, which in this case is the budget. And if it is this side of the line, it is favorable. If it's on this side of the line, it is unfavorable. Now this one's a little bit interesting because this one's looking at positive and negative values. The positive numbers are my revenues. The negative numbers are my expenses. So if I have a larger negative number, I spent more money than I expected. If I have a larger positive number, I have a favorable sales variance. Here I can say, okay, I've got all these nice favorable variances, but I've got a lot of these that are unfavorable in January, February, and I can go down and figure out, okay, is that from the price or is it from the volume that's driving that number? So this is just a visualization of those, nice little tables that you were generating in your managerial accounting course, your strategic cost course. You have some benchmark, some goal that we're expecting, and then we compare it against another one. Another interesting analysis here, this one's called Benford's Law. And Benford's Law basically says that if you look at a large set of transactions, a large number of numerical transactions, that they are going to follow a specific pattern. This blue line is my predicted distribution of digits. And this is looking at, this is frequently called the law of first digits. So the intuition behind Benford's Law is that I am more likely to buy things that cost $10 than $90. Or if you go up, you make a lot more $100 purchases or $200 purchases than $900 purchases, 1,000 versus 9,000. All of these numbers will follow the same distribution. So here, looking at all the employee transactions, I see that this is normally what happens. Now, I see that 4 is elevated. I'm having a lot more 4 transactions than not. Here's one example of why that might be. In this company, I may have a policy where anything over $500 requires approval. So as an employee, if I'm using my P card to buy things, I'm going to make several $400 and something purchases to get around that. I'll just split it between 480 and 400 and whatever. Now the person knows, the employee knows that if they make a whole bunch of $499 purchases, that sure is suspicious, right? Because you're like just right below the level. But if I make a $483 purchase and a $472 purchase and a $465 purchase, those look pretty random, right? More random than just $499. The problem is they all start with 4s. So even though I'm trying to, be clever and create these $400-something transactions, it's popping this Benford's analysis. And I can go and look at all those $400 and I can identify the employee who is skirting my control, if they are. So again, I wouldn't expect my transaction, I wouldn't expect to have a whole bunch of $400 transactions if this is if they're following normal procedure. By the way, Benford's Law is really cool. There's a website, testingbenfordslaw.com. The pink value here, this is my predicted value for Benford's Law. Twitter followers by count. You're more likely to have 1 follower than 9 followers, 100 versus 900, 1,000 versus 9,000, etc. People wounded by terrorism. Or the population of Spanish cities. That's with 9,000 cities. Google Book unique words. Loan amounts on kiva.org. That one's this one's a really interesting one. These are loan amounts. Notice that the 5 pops out. It's much higher than the predicted value. These people, I guess, are more likely to request $500 as opposed to $400 in a loan, right? It's a nice round number. Number of Sunni Muslims per country. Another interesting one that doesn't follow this pattern. Common iPhone passcodes. Why wouldn't iPhone passcodes fit this model? People use patterns. right? And people usually start in the same zones, either the corners or the center. So you're not going to have 4 very often. People are going to start with 4 or 6. So we start with a 5 or we start with a 1 or a 2. It doesn't always hold true, especially when you're generating the numbers purposely. But for random transactions or random values, it's going to have a fairly consistent following. So Benford's law. I have some graphs down here. This one is also diagnostic. This is clustering. With clustering, what I'm trying to do is I'm looking at all of the data and I'm trying to group it into people that might be similar. So if you look at like a target example, I might look for older people who need medication. So I'm trying to find a center and grouping these all into that group. Or I'm trying to find, new mothers so I can sell them baby stuff. Or college students so I give them all the cheap furniture and pillows and stuff when it's back to school. Here's another example of clustering. So in this case, this is looking at insurance payments. And so we look at the payment amount going up on the vertical axis and the days to pay. So we could use clustering to try and identify groups like, for example, this one here. That one's really interesting. I have payments that are very high, but I'm taking a really long time to get them their money. So I might say, okay, what is it about those individuals or that process? Like, why are we delaying payment on those when we probably ought not to? Okay, these are small amounts that take a long time to pay. These ones are big amounts that take, they're just big amounts, so we don't have a lot of huge. With clustering, what it's doing is it is going to take all the observations. It's going to calculate the center that is going to minimize the distance between the observations. So we basically minimize this function to get all the observations that are in that area. The thing that you input is the number of clusters. Say I want, in this case, 8 clusters. It's going to do that calculation for doing that. But it's basically just calculating the Euclidean distance and stuff. It's fun. We just let the program do it for us. But again, you can see with clustering how we could make some general assumptions about those groupings, right? These are all just normal people. We don't necessarily care about those, but we care about the outlier ones, the ones that stand out from the mass. This is why it's, again, a diagnostic analytic. What's different about this one from normal behavior? So from there, we get into predictive analysis. Okay, predictive analysis, the most common one that you have probably experienced is regression. You do a scatter plot. Think about mixed costs in managerial accounting, where you set the levels of volume and the cost to figure out how much of that is your fixed versus variable. Fixed being the y-intercept, variable being the slope. Okay, so we set some sort of line. And the reason we do that is because we know what's happened in the past. Now we have a new observation where the volume is this. We want to know how much it's going to cost us, so we can predict what it's going to be for the next month. We set those variable cost or the mixed costs so that we can predict what those cost calculations will be in the future. You also do a lot of this in financial markets. Right? You're trying to predict stock market returns based on, or your portfolio returns based on a beta value and other independent variables that you care about. In academic research, we do a lot of this in figuring out, is stock market return tied to diversity of the board of directors? And then over here on the left, we have classification. With classification, we look at observations, and we want to decide what is going to be in class A or class B, and we set a decision boundary between the two. So instead of predicting a specific value, we want to predict whether it is, fraud or not fraud. And this can get a little bit more interesting because depending on how far away the observation is, this one is highly likely. We can set things like fraud scores to identify that transaction versus another. Okay, you think about using your credit card. How many of you received a fraud alert on your credit card? They send you a text message and say, hey, we noticed this activity. If you buy breakfast in Pittsburgh and then buy a shirt from Express in Las Vegas in the afternoon, they're going to say, hey, that's not inside of your normal behavior. So we'll pause the transaction, make sure that you confirm it, and then once you confirm it, we'll let the transaction go through. Or alternatively, we'll pause the transaction. If you say it's fraud, then we will stop it from charging you and us losing money. So classification and regression are the two main categories here. Speaking about classification, when we decide this decision boundary, the complexity of the model may not be terribly predictive. So all of these little green squares and blue circles that are in the wrong, these are errors. Here we have an underfitted model. meaning we're getting quite a few errors. The more complex the calculation, the more precise the calculation, we can reduce the errors. But the goal is not always to get rid of all of the errors. If we have an absolute model, is using every precise observation from the past, and then we come and predict a new value, this is what we call overfitting. And it actually is less predictive because it's hard to tell whether that should be a square or a circle just based on the way that we've calculated the model. The only thing you need to know here is that we don't want it to be too simple. We don't want it to be too complex. We want to find that nice balance. And if you want to learn all about this, by the way, we're talking about data analytics in 2 class sections. I have a full 15-week course in the master's program that talks about data analytics in accounting and does this a little bit more in depth. You can also take other classes in that as well. We're giving you just a high-level overview. And then finally, we have our prescriptive analytics. Okay, prescriptive analytics, these are recommendation engines. So this would be, for example, when you watch Netflix, although Netflix is not as good at this as it used to be. They just recommend all the originals. So Netflix, you watch a show and it says, oh, you saw that you like that. You might be interested in these other shows that are similar. Amazon does a really good job at prescriptive analytics. You bought this. Other people who bought this also bought these other things. We think that you'd probably like this as well because it matches your purchase history. Okay, so we're making recommendations. A lot of this pulls into artificial intelligence. One good example of AI in accounting is an audit opinion. Okay, if I have an audit partner who has given opinions, and I can observe the past opinions of this audit partner, given certain inputs about the company, like the number of corrections that they had to make, the number of issues that they had, to figure out whether they are going to give an unqualified, qualified, or an adverse opinion. I could build a model that would analyze a company's audit report and predict fairly accurately whether the audit partner would give them an unqualified, qualified, or adverse opinion. If we can create these models, why do we need audit partners? We're not there yet. But this is an example of using that. Okay, and artificial intelligence just takes this model and keeps improving it as we get more and more observations. If you've had an iPhone for the last 7 years, you know that Siri has gotten better at responding to your queries, both in interpreting your speech as well as like giving you relevant stuff. That's because they are learning from these models. The more you speak at it, the better it is at predicting your individual voice, for example. We don't do a lot with prescriptive other than just mentioning it's there. I just want to show another example of classification real quick. It used to be, if you were doing photos with your digital camera, you would have to go through and you'd have to categorize the photos. You'd have to put them into folders, you'd have to tag them with people, you'd have to figure out what objects and events were in those. And oh, look, Halloween, that's cute. And so now we've gotten to the point where you don't have to do that, because if you come in here and say I search for something like yellow car, I've not tagged any of my photos with yellow car. And yet Google can fairly accurately look through all of my hundreds of thousands of pictures and find pictures of me with my yellow car. Hey, look, there's a yellow car. There's a cab right in the background there. See, it's like I like yellow or something. Okay, this is my yellow car. It can do a fairly good job of predicting these things. If I go in and search for Disney World. Okay, we did a Disney year a couple of years ago. If I search for Disney World, I haven't tagged these, although you'd say, well, if you use your phone camera, it has geolocation information, so it has the coordinates of where you're taking pictures, and you'd say, oh, that's Disney World. But these are taken with my SLR camera that doesn't have a GPS device, and it can still find pictures of Disney World fairly accurate. Although, here's Phipps, but you could see why it would classify that as Disney World, right? Because it has a castle with spires, and it's, it's not always 100%, but it's pretty darn good. Okay, so these are classification models where Google has trained images. Somebody went through these, like a whole bunch of pictures, and said, that's a yellow car, that's Disney World, that's whatever. And somebody had to train these models. A lot of you have trained these algorithms when you tag your friends on Facebook. Google gets really good at facial recognition when you say, oh, that's my friend, and it says, is this your friend? Because you tagged that one. And so the more in fact, a lot of the training for these photo programs comes from Instagram, because people have been really good at tagging photos with Instagram, like what's in the photo, hashtag blah. And so they use that to train these things. Whenever you have one of those websites where you try to log in and it says, identify the traffic lights, you know, those CAPTCHAs, those are models that you are training to identify. You're helping the robots win someday in the future. There's some really interesting things, really interesting applications that we can use with these different types of analytics.